Back for the rest of chapter 6, we're going to start with a video.
Confidence intervals. In order to understand confidence intervals, we need to understand sampling and sampling error. To find things out about a population of interest, it is common practice to take a sample. A sample is a selection of objects or observations taken from the population of interest. For example, a population might be all apples in an orchard at a given time. We wish to know how big the apples are. We can't measure all of them, so we take a sample of some of them and measure them. To find out about different sampling methods, see our video, Sampling, Simple, Random, Convenience, etc. Inference is when we draw conclusions about the population from the sample. Because the sample is only a selection of objects from the population, it will never be a perfect representation of the population. Different samples of the same population will give different results. This is called sampling error or variation due to sampling. There will always be sampling error. Confidence intervals. When we express an estimate of a population parameter, it is good practice to give it as a confidence interval. A confidence interval communicates how accurate our estimate is likely to be. Say we wish to find out how big the apples are in our orchard. We put this as an investigative question. What is the mean weight of all the apples in the orchard? We take a sample and calculate the sample mean. This is the best estimate of the population mean. We use a confidence interval to express the range in which we are pretty sure the population parameter lies. In this case, the population parameter is the mean weight for all the apples in the orchard. What affects the width of confidence intervals? The width of a confidence interval depends on two things: the variation within the population of interest and the size of the sample. Variation in the population. If all the values in the population were almost the same, then our sample will also have little variation. Any sample we take is likely to be pretty similar to any other sample. Our estimate is going to be pretty close to the true population value. We would have a small confidence interval. But a more varied population will lead to a more varied sample. Different samples taken of the same population will differ more. We would be less sure that the sample mean was close to the population mean. Our confidence interval would be larger. So, greater variation in the population leads to a wider confidence interval. Sample size also affects the width of a confidence interval. If we take a small sample, we don't have much information on which to base our inference. Small samples will vary more from each other. There is more variation due to sampling or sampling error with a small sample. In larger samples, the effect of a few unusual values is evened out by the other values in the sample. Larger samples will be more similar to each other. The effect of sampling error is reduced with larger samples. When we take a large sample, we have more information and can be more sure about our estimate. The confidence interval can be smaller. There are several methods for calculating confidence intervals: informal, traditional normal-based formulas, and bootstrapping. When we use traditional confidence interval formulas, the stated level of confidence also affects the width of the confidence interval. All estimates of population parameters, such as means, medians, differences of means and differences of medians, should be expressed as confidence intervals. You can learn more about how to calculate confidence intervals in our other videos.
And we will watch this other one because it's well done. So, briefly go over. Whenever we're trying to estimate anything about the population from a sample, our sample statistic is our best guess at the population parameter. But that one number, point estimate, is never going to be perfect. No sample will perfectly represent the population. Samples will vary one from another. This is the idea of a standard error for the mean, the sampling distribution, and sampling variability. So it is always better when we try to estimate something that we not just give the point estimate, a single number, but also a range of numbers that we are pretty sure or highly confident that the truth lies in. Now, when we give this interval, it acknowledges that there is some uncertainty And we don't know for sure what the population parameter is. And that video talked about different things that affect how wide or how big the confidence interval is. Amount of variability in the population or the sample, the standard deviation, the size of the sample, n, and the level of confidence, whether we want 90%, 95, or 99%. So let's watch another quick 4-minute video.
To confidence intervals. In inferential statistics, we study a sample and use the results to draw conclusions about its population. Suppose I want to estimate the average age of students at a college. So I choose a random sample and find the sample mean age to be 23. This sample mean of 23 is called a point estimate of the population mean mu. So a point estimate is a single value, that is, a statistic computed from sample data and used to estimate a population parameter. Because a point estimate is a single value, we can't really tell how good it represents the population. So in inferential statistics, we prefer to use an interval or a range of values to estimate the population parameter. For example, suppose we found that the mean age of students at the college lies between 21.5 and 24.5. This range of values is an interval estimate which we refer to as the confidence interval. We refer to the smaller value as the lower confidence limit, LCL, and the higher value as the upper confidence limit, UCL. This interval was actually obtained by taking the sample mean 23 and subtracting and adding 1.5 to it. That is, 23 minus 1.5 gives 21.5, and 23 plus 1.5 gives 24.5. The 1.5 is referred to as the margin of error or error bound. Different letters like E, B, and M are used to represent it, but let's just use E. In essence, the confidence interval estimate for a population mean lies between the sample mean minus the margin of error and the sample mean plus the margin of error. The margin of error is calculated based on a confidence level. The confidence level basically refers to the percent of confidence intervals from many samples that we expect to contain the true population parameter. Confidence levels of 90%, 95%, and 99% are often used, but 95% is the most commonly used confidence level. To illustrate, suppose the true population mean age at the college is 22.5. If we select 10 samples of the same size and construct 10 confidence intervals at 90% confidence level, we will expect 9 of the 10 to contain the population mean. And with 95%, we will expect 19 out of 20 intervals to contain the population mean. Now, suppose the interval 21.5 to 24.5 was obtained at the 95% confidence level. To interpret that, we say, we are 95% confident that the true population mean lies between 21.5 and 24.5. Note that it will be incorrect to say that there is a 95% chance that the population mean lies between 21.5 and 24.5. What the 95% confidence interval means is that if we select 100 samples of the same size, 95 of the confidence interval obtained from them will contain the population mean. This interval from 21.5 to 24.5 here is just one of those 100 intervals.
Okay, so I want us to look at this figure here. So if we constructed, or if we took 100 different samples, that each of those 100 samples would have its own confidence interval because it would have its own mean and its own standard deviation. They would likely be similar to each other, but not exactly the same if we're going out to more than 2 decimal places or 1 decimal place. However, we never know, we're never certain which confidence interval we are getting. Now, at the 95% confidence level, 95 of these intervals would contain the truth. These are the blue ones. 95 of them contain the truth. But there are 5 that don't. 5 out of every 100. Those are the ones that are marked in red. Now, if we only take 1 sample and construct 1 confidence interval, we might happen to get a blue correct one. We might happen to get a red incorrect one. There's no way to know for certain. I think this is the biggest thing I want to stress. We never know when we're making an error. We always want to do whatever we can to not make an error, but you can never know for sure. And this is why replication is so important in research. We might accidentally get one of these red ones that does not have the truth in the confidence interval. There's no way to know for sure. Now, people say, well, why don't we make it 99% or 99.9% confident? There is a give and take. The more confident you are, the wider the interval will be, all other things held constant. And so, sure, we can be 99.99% sure, but the interval will be so wide, it'll be like between 0 and 100%, between a height of 1 foot and 10 feet, that it won't be useful. So that's why 95 is usually the most common confidence interval level, because it's a balance of being fairly sure and fairly certain without being so wide that the confidence interval is not telling us anything. Okay, we have one more of these to watch.
Or a mean using a formula. To find out about confidence intervals, watch our video Understanding Confidence Intervals.
We did.
This video introduces the traditional way to find a confidence interval for a mean using a formula. Usually, we just get the computer to calculate the confidence interval for us, but it is useful to know what is being calculated. Two things will affect the width of any confidence interval: variation in the population and sample size. We don't know the variation in the population, but the variation in the sample will be an indicator of the variation in the population. We use the standard deviation for the sample as a measure of variation in the population. The standard deviation tells us the average distance the values are from the mean in the sample. The central limit theorem underpins the following formula for the confidence interval of a mean. We take the sample standard deviation and divide by the square root of the sample size. This gives us the standard error. Say we took lots of samples of size n from the same population. The standard error is a measure of how spread out we would expect those means to be. It is interesting that we divide by the square root of the sample size. This reflects the phenomenon that the more information we have, the less new information we get from one more observation in the sample. It makes sense that increasing our sample size from 10 to 20 will give more information and thus decrease our confidence interval more than increasing the sample size from 100 to 110. In traditional confidence intervals, we also wish to specify the level of confidence. The more confident we wish to be, the larger our confidence interval will be. If we wanted to be certain of including the population parameter, we could use a very wide interval, but that would not give us any useful information. We use a value from the t-distribution in our formula. You can read these off a table. The value of t depends on the sample size and the chosen level of confidence. The bigger the t-value is, the bigger our confidence interval will be. Here are some t-values for different sample sizes and confidence levels.
I don't like this.
We multiply the standard error by the t-value to get the margin of error. So now we add and subtract the margin of error from the sample mean to find the confidence interval. This confidence interval gives us a range of values that we can be pretty sure or confident contains the mean from the population. We can explicitly state how confident we are. It is quite possible that this interval will not contain the mean of the population, but usually a confidence interval will contain the population parameter we are estimating. Here's an example. We wish to estimate the mean weight of apples in the orchard. We take a sample of 15 apples from the orchard. These are their weights. This combination box plot and dot plot shows the distribution of the sample. We use Insight to get these summary statistics. We can see the mean value of 149.3 grams, the standard deviation of 4.758, and the sample size of 15. We wish to find a 95% confidence interval for the mean weight of apples in the whole orchard. We substitute the appropriate values into the formula. The standard error is 4.758 divided by the square root of 15, which gives us 1.22851.
standard error.
The t-value for a sample of 15 and a confidence level of 95% is 2.145. The margin of error is 2.63515, which we round to 2.6. We add and subtract this from the sample mean of 149.3 to get a confidence interval of 146.7 to 151.9. Thus, our 95% confidence interval for the mean weight of the apples in the population is 146.7 to 151.9 grams. This is not the interval that will hold the weights of 95% of the apples in the orchard. It is the interval that we are 95% confident will contain the true, unknown value of the population mean. If we were to take lots of samples of size 15 and create 95% confidence intervals from them, we would expect most of them, 95% of them, to contain the true population mean. However, about 5% of them will not contain the true population mean. We do not know for certain whether our confidence interval really does contain the population mean. We can be 95% sure that the mean weight of the apples in the orchard is somewhere between 146.7 to 151.9 grams. A much quicker way is simply to get the computer to calculate the confidence interval. Note that the answer here is slightly different due to rounding. You should never give confidence intervals to too many decimal places. This video was brought to you by Statistics Learning Centre. Visit our website.
Okay, let's get going. The next few slides. Oh, okay, there is the crash course statistics video here that I'm including on this slide. This is slide 29, but it's 13 minutes long. And most of the things in it we've already gone over. But if you're still struggling with confidence intervals, I highly suggest this video. It's really well done. But in the interest of time, we're going to move on. And I'm going to hold off on the Shiny app and the other applet on the website, and we're going to do those in class. They just are interactive ways to play with or get the hang of confidence intervals without getting bogged down too much in the rote math. So let's go over the formulas for all confidence intervals. And today we're doing confidence intervals for a mean, but in the future we're going to do confidence interval for the difference between two means or other values. So there's a general format for all confidence intervals. We always start with the point estimate, our best guess, and then we add or subtract some margin of error that is our plus or minus how uncertain or how certain we are. And so it's always the point estimate plus or minus our margin of error. Every margin of error has two parts to it as well. It's dependent on our critical value and the standard error for whatever we're measuring. The critical value is either a Z or a T score that we look up in the table. The standard error, we're going to use a formula, and it depends on if we know the population standard deviation, and then we want to use that. If we don't, we'll use the sample standard deviation. So if we do know the whole population standard deviation, and or we have a very large N in the hundreds, we would use a Z critical value and that sigma that we do know. And the Z critical value we look up in the table, we would multiply it by the sigma over square root of N. That gives us our margin of error that we would add or subtract to our best guess X bar. That's the sample average is our best guess at mu, the population average. That's what we learned. Those are the things that we learned in chapter 5. But now in chapter 6, we've introduced this idea that if we don't know sigma, the population standard deviation, we can use the sample standard deviation, S, in its place. But if we do that, the Z does not fit very well, and so we need to instead use a T value. So if we do not know the population standard deviation, or we have a smaller sample size, like under a couple hundred, we should, instead of a Z critical value, use a T critical value. And then we can use S, the sample standard deviation, divided by the square root of N for our estimate of standard error. So when you construct a confidence interval, you have to have data to get X bar and S, our sample's mean and our sample standard deviation, and the sample size. Then we have decisions. We need to decide, are we going to go with the standard 95% confidence interval, or are we going to do less or more? There's reasons why, but we're always going to default to 95% if there's no other good reason, because that's the standard in almost every field. Then we need to find a critical value, and that is based on that confidence level as well as degrees of freedom. Always confidence intervals are 2 tails. Always 2 tails on the t table. And then we're going to calculate our endpoints. Now remember, if we have a larger sample, it's going to be more tight confidence interval. If we have a smaller sample size, we're less informative, we're going to have a wider confidence interval. Also, if we want a 99% or a high percentage confidence, it's going to have to be a wider range. If we're okay with a 70 or 80% confidence, it'll be a narrower range. So these formulas are also on our formula sheet. So again, this is the one we looked at before in our previous recording. So the confidence intervals are over on the left-hand side. So we're always going to start with our estimate. We're going to do sample mean x bar. Then we're going to add or subtract either a z or a t critical value. On this formula, they have a little asterisk. That means critical value. And then we're going to times by our standard error. And depending if we know sigma, we'll use that. If we don't, we'll use s. But remember, if we're using the sample standard deviation, that's paired with a t. If we know the population standard deviation, then we can go with the z. So let's go back to our example we were working on before and construct a confidence interval. And we're going to go with the default 95% confidence interval for the number of visits that each patient makes to their doctor in a year. And we have 10 values. So our sample size is 10, and we used R before to calculate the mean and standard deviation. But to make that confidence interval, we've got to find a critical value in the table. Since we don't know the population standard deviation, and we're going to use our computed sample standard deviation, we're going to need a t critical value instead of a z critical value. And remember, on this table, we have to go with the degrees of freedom line that matches our data. Now this sample size was 10, so we're going to go to the line for 9 degrees of freedom. So we go down to that line of 9. Confidence intervals are always symmetrical, so they're always 2 tail. 95% confidence interval is matched with alpha 0.05. So that tells us the column to look in. And this is the same number we found before, 2.262. That was our critical value for an alpha 0.05 test. It's also our critical value for the 95% confidence interval when we have 9 degrees of freedom, or a sample size of 10. So we used R before to find that our sample had 10 observations in it with an average of 7.6 and a standard deviation of 4.25. Those were numbers that we calculated based on the sample. Now to do the confidence interval, we're going to make it with the point estimate, average of 7.6. That's our best guess. Then we're going to plus or minus the t value we looked up in the table, 2.262, times our standard error. And our standard error is going to be the standard deviation divided by the square root of the sample size. When we put those together, we get a range of values. When we subtract, we always get the lower end or the lower bound. So that's 4.56. And when we add our mean plus t times the standard error, we get the upper end or the 10.63. So for this example, our confidence interval would range from 4.56 to 10.64. I would never give more than 2 decimal places on a confidence interval. In fact, often we'll use 1 less decimal place on a confidence interval than we do for, say, the average and the standard deviation. And that has to do with over or understating the amount of information a confidence interval gives us. So we usually write it with the smaller number first, followed by the bigger number. Now, on this slide, I've done the calculations with R, but you can do them by hand just the same. I like R because I'm less likely to push a button wrong. So this slide's pretty much a review, except for the meaning. The meaning of a confidence interval is not 95% sure that that range has the truth. We're not 95% sure that the truth is in that range. What we are true is that 95% of samples would make confidence intervals that contain the truth. There's a 5% chance that our confidence interval does not contain the truth. So it's not that confidence intervals are bad, just like p-values are not bad, but we need to make sure that we're stating what they mean and what they don't mean. So when we go to write up our test for APA style, if we're doing a Z or a T test, If we're putting means and standard deviations in our sentences, in parentheses, we can use that capital M that's italicized. If we're saying the mean in the sentence, we would want to write out the word mean. The Z and P value, if they're in the middle of the sentence, you set them off with commas, not parentheses. And if they're at the end, we leave them just set off again with commas. T and Z values, usually we go to 2 decimal places. P value to 3 decimal places, unless it's P is less than 0.001. You should never write P equals 0.000. That's one of my pet peeves about SPSS. SPSS program, if you have a tiny P value, it says 0.000. It makes it look like it is equal to exactly 0, when it's only just a very small number. So I think I'm going to throw in the R on this one. Let's go for it. So we're going to use the cancer data set that we've seen before, and I have it cleaned up. And so we are going to do some tests here, some t-tests for the mean. So let's look at this data set. We have an age variable. These are middle-aged people. We also have a weight in pounds, stage of cancer they're in, 1, 2, 3, 4, etc. So let's ask the question, do patients weigh more than 160 pounds at intake? So we can use that weight variable that has how many pounds, and we want to know, is it greater than 165? Now the research question is stated here directional. It says specifically more than 165. But due to tradition, we're going to do a two-tailed test, which is the default. So this code's going to look very similar to a lot of the code we've seen before. We're going to always start with the name of the data set, and then we are going to pipe it into, we need to pull out the variable we're concerned with. This is how you do a one sample test. We did the same thing with the Shapiro-Wilks test. So we are going to use dplyr pull and pull out the name of the variable we're concerned with, and then pipe it into a base function called t.test. And we have to tell it what our null hypothesis is. Mu equals, in this case, 165. So this code is going to run a t-test to see if we have evidence that the weight is different than 165. Again, the default is to do a two-tailed test, and we're going to go for that. Now, we get a little bit of output out of here, so let's break it down. It tells us that we're doing a one-sample test. It says data equals dot, and that happens because we're piping the data from above. Don't worry about that. And then it gives us our test results. Then there's 3 parts of our test results. There's a t-value, the degrees of freedom, and the p-value. So let's look at the degrees of freedom first. Since the degrees of freedom are 24, that tells us the sample size is, well, that came from n-1, so the sample size must have been 25 in order to get degrees of freedom 24. And you can look back at your data set, and there were indeed 25 observations in this data set. So it makes sense that the degrees of freedom is 24. You always want to check these things to make sure that nothing went wrong. Then here's our t statistic and our p-value. Now notice when we use the table, the t-table, to find a p-value, we could only say it was between this number and that number. But when we run a t-test with computer software, it will actually tell us our p-value to many decimal places, and we don't end up with the range idea. Now, it does alert us that the alternative hypothesis is that the true mean is not equal to 165. So it spells it out that the alternative is not equal to 165. And our alternative, our null hypothesis we stated was mu is equal to 165. It also, by default, is going to give you the 95% confidence interval without you lifting a finger, and it will also give you the sample statistic mean of 178. So with, let's see, 1, 2, 3, 4, 5, 6, 7 words, basically, we've gotten all this calculations done for us. So on the homework, you'll be writing some code to produce the output for practice, but you will also be asked to look at this output and write a conclusion. And that's the part that you will be required to do on the test, because running the test is one thing, but knowing what it's telling us is quite another. So again, what were we asking? We were asking whether patients weighed more than 165 pounds, actually as a two-tailed test. So do patients weigh a different amount than 165 when they're at intake of the study? So our answer is, well, we look at our p-value, and we're going to go with the standard alpha equals 0.05 significance level. And so we ask, is the p-value small? And yes, it is small, as in smaller than 0.05. So this does provide evidence against the null hypothesis of an average being 165. Now, even though our null hypothesis and our alternative hypothesis allowed for a two-tailed test, if we do in fact have statistical significance, our conclusion needs to say which direction we found the effect in. So even though our alternative hypothesis, the alternative said the weight was different than 165, we are going to specify that yes, the average, we have evidence the average is, well, let's see, it's 178. That's bigger than 165. So our conclusion better say that we have statistically significant evidence that these patients weigh more than 165 at intake. So a sentence in APA format could look something like this. The patients in this study, and we are going to also say how many there were, weigh, and then there's a sample statistic, 178.28 pounds, which is significantly, because our p-value was significant, more than, because this 178 is more than 165 pounds. Now, if we're using any of those abbreviations of N, M for mean, and SD for standard deviation, in parentheses, they're for those abbreviations. But the test statistic results always are not in parentheses. So when we give a T, a P, and a CI for confidence interval, those are italicized. After the T, in parentheses, we say our degrees of freedom. So T has 24 degrees of freedom, and the value is 2.08. The p-value we're going to give to 3 decimal places, nothing in front of the period. And then this is the new part. For the confidence interval, we put 9.5% space, CI in italics, and then in square brackets, we put the lower and upper intervals with the comma between them. So that would be this middle part of our output, our 95% confidence interval. Now, by default, it's going to do a 95% confidence interval. If you want a different size confidence interval, you can change the default. There's an option that you can add into the tTest parentheses. It's conf.level, and you make it as a decimal. So if we want a 99% confidence level, we have to put conf.level equals 0.99. You don't put 99%, you put it as 0.99. I've had a problem with this myself in the past. So you will see that you get identical output. Our average of our sample is still the same. Our T statistic observed, our degrees of freedom, and our p-value observed, that's all identical. When we change the conf level, all it does is change the middle part that has the confidence level interval listed. Everything else is the same. So we would write it up exactly the same, except for it would change to a 99% confidence interval, and it would change the numbers that are inside the square brackets. Now we can use this polling of a variable and doing a t-test in combination with all the other steps that we've learned. So we can do this on a sub-sample in our data set. So maybe I'm only concerned with the weights of patients who are in advanced stages of cancer. So maybe I only want to look at or investigate the intake weights for those patients that have cancer stage 3 or 4. So I can do that by, after stating which data set I'm using, filtering out to only take certain subjects. So I'm going to require that the subjects are in stage 4 or 3 before I pull the weight variable and run the t-test, comparing their weights to 165. Again, we've been learning lots of different building blocks, and we can assemble them in whatever order will answer the question we're looking for. But you do have to make sure you filter the people in your study before you pull the variable out, or else it won't work. So here I've ran the code, and here's my output. It looks the same format, but the numbers are different. Our average here is 178.25. Was that exactly the same? Nope, it's slightly different, but very close. But here's our t-value. Our degrees of freedom are now 5. If the degrees of freedom are 5, how many people are involved in this test? Degrees of freedom are sample size minus 1, so it must have been a sample size of 6. There are only 6 subjects that are in stage 3 or 4. That's a lot fewer patients. So we'll notice that our confidence interval is actually much wider than it was before. It goes all the way down to 137 and all the way up to 219, where before it was much narrower in width. So we could write this up. Now, this case, our p-value is not tiny. Our p-value is way bigger than 0.05. So this is not any evidence that these patients have a different weight. So with a two-tailed test, if there is statistical significance in our results, we state the direction. But if there is not statistically significant results, then we just stay with the two-sided alternative. So we could say the patients in the study with stage 3 or 4 cancer, which is only 6 of them. Now notice I'm using the little n. The little n refers to it being a subsample or part of our sample, where the capital N usually is saved for when we're talking about the whole sample. And that's an APA distinction. So this N of 6 has an average of 178.25, but that is not statistically significant evidence that the average weight is more than or even different than 165. Usually, if our p-value is not significant, we usually leave it there. But it's always advantageous, and we probably should more than we do right now in research, is add the confidence interval afterwards. And that goes along with the American Statistical Association and the American Psychological Association's commentation from their task force on how to not over-rely on p-values, is to also include those confidence intervals. And really, when your software is already outputting them, it's not a lot of more energy to put them in. And so that's something that's going to really help your field if we get used to adding these confidence intervals in addition to p-values. And so there we go, chapter 6.